How are you? Today, good? Yeah, excellent weather for another lecture in deep learning. I hope you agree. Uh, Somehow fewer people today. Anyway, so for those who still with us, so today's lecture is about regularization, and the plan for today is to discuss the point of regularizing deep neural networks. So what we would wish to do, what we can do, and to discuss some explicit regularization techniques. So the common ones, like L1, L2 regularization and data augmentation and dropout, but also to at least for these basic techniques to understand what they are doing for the classical models and for the deep models. And yeah, is also like the plan to have some discussion about implicit regularization and this sort of things. So I would like to start maybe from this example. That is a training of classifier for some image classification problem. This is the CFR10, so some small images of 10 classes, down kind of subselected and down sampled from the ImageNet. And what we can experience in practice is that, so you see here these plots, they are done with two batch sizes, like a smaller batch size and a larger batch size. We will talk about this a little bit also. But for now, let's look at this orange plot, for example, in each of these graphs. So for the batch size 32, we have some finite training data set. It's like 50,000 image examples and large enough model. So we are in kind of this in over parameterized mode, that the model capacity is quite big. So we are able to really minimize this training loss down and down. And we are able to maximize the training accuracy, so to reach like 100% classification on the training set. And if we assume that the training set is clean, this is sort of actually natural. What we would want our model to do is to at least be able to classify all of the examples that we have correctly. Why not, right? So this is not a fault in itself that we are that we are classifying all of the training data correctly. So that is not an overfitting issue. It's actually maybe desirable in this case. But what is an issue is maybe that the validation accuracy could be going down if we train longer and longer. So if after we have fitted to the training accuracy, so then the validation accuracy may be dropping down, and this would indicate that we are fitting too much to the training data, whereas this does not give us a good generalization to the validation data, and that's a bad issue. So here it is not happening by some reason, more or less automatically. But what is happening is that the test loss starts growing. And then you might be wondering, okay, what does it mean? Is that bad? And so what's going on here? So for this example, I think like a good analogy is the case that we discussed through the labs and the seminars when we had when we discussed just linear models. So if you have some training data in this space and the linear model that we optimize by the gradient descent. So suppose we start from some linear classifier like this, so that does not separate the data well. Then through the labs, I think we discussed that the gradient descent would converge to the maximum margin solution for this separable training set, and it would do so for many loss functions, for not only for the negative log likelihood, or okay, so for couple of loss functions. So let's see. Yeah.
I'm quite certain there was like some condition for the weight initialization initialization maybe or something for the gradient descent to actually converge to like the maximum margin solution, or was there not?
Yes, you're right. Yes. So.
And what was that? I'm just like, I remember that there was something, but I don't remember what exactly. Like, what is the condition for gradient?
It should start from 0 weights.
Okay. That's everything.
Yeah, so suppose this is like our maximum margin solution, and what we kind of imagine from this logistic regression an example and its understanding is that the decision boundary goes here, right, with more training. While also the norm of this weight vector, so the norm of that vector, maybe we start with a small norm, but then with more iterations, the norm grows for the, at least for the negative log likelihood training. So the norm would be growing, and that for this solution, so this is our limit, like maybe the dynamics of gradient descent is that, yeah, so then the norm would be growing. So for the linear regression, we did not have this issue. Okay, anyway, what my point is that when the norm is growing, we are getting here sort of, we are going from sort of smooth predictive probabilities to harder predictive probabilities. So the predictive probabilities are assigned, so if you are far away from this hyperplane, how big probability, how big confidence it assigns to its decision. So that was kind of dynamics for linear models, and it kind of fits here to these plots as an explanation as well. So when we reach the 100 training accuracy, so we are kind of slowly maybe improving the training accuracy, and maybe we've reached already 100% training accuracy, but we could still go on, and the decision moves to the max margin solution, and the test accuracy still improves. So we can kind of have already the training accuracy 100%, and while continuing learning, we could kind of still improve the decision boundary. But at the same time, this prediction becomes overconfident, and then this improves the training loss a little bit, being more and more overconfident. But for the test loss, if it happens so that some test example is on the wrong side of this decision boundary, or then it's a huge penalty for that, right? So it is this top plot. It actually reflects that while we are still moving to the better separating hyperplane, we are becoming overconfident, and this test likelihood predictions, and these effects, they are kind of happening at the same time, right? So it's like we are not yet reached the 100% training accuracy, while the test likelihood already starts to be estimating poorly. Yeah, so these are like our kind of one case of the training mode of neural networks, and even the worst case would be that when here the validation accuracy would be start falling down, because it is not guaranteed, it's not ensured what will be the dynamics for a deep network. And yeah, we would like then maybe to regularize somehow this. And already from this image, you can see that things like batch size for stochastic gradient descent have substantial effect on the training and on your generalization, so on your validation set performance. So it appears to generalize better, and if we train with a smaller batch. Okay, also from this plot we see also the training was more efficient and faster to reach 100%. But it's already you could see that, yeah, there is a lot of things having multiple effects, and the training process, the training procedure and its hyperparameters are going to affect on the what behavior you get, and whether how well it generalizes, and so on. So, but yeah, this is like the kind of problems we want to deal with. And we will discuss sort of 3 approaches to this: so parameter regularization, data augmentation, and sort of injected noises. And now we start with parameter regularization. And maybe kind of like a bird's eye view on the problem from the theoretical side. What is the best we could do about parameter regularization? So what is the best we could do about this problem where there are multiple solutions that fit the training data well in terms of the likelihood, and we sort of need to learn in this setting and predict well in this setting. So the best what we can do is given by Bayesian setup, maybe quite arguably. And I just propose to recall this setup and discuss a little bit so how it relates to the other things we are going to be doing. So the Bayesian setting is considering that our model that we are going to train, so that the parameter is not some kind of uniquely given vector of values, but it is treated as, or rather it is modeled as a random variable. So it's kind of statistical unknown, and if it is treated statistically, we can specify our knowledge about the parameter not only by just a concrete value of the parameter, but we can specify a distribution. So what parameters are more likely, what parameters are a priori are good for our problem, and what parameters are not as good for our model. And this works well for these classical type problems like you know, you have the Bernoulli distribution, and you know there must be at least few socks of both colors. Or you have what else? Yeah, you have maybe this German tank problem with, and you know a priori that Germany could have not produced more than certain number of tanks, and so you have some bounds, and then you say, okay, the number is somehow maybe uniformly distributed within these bounds. So you kind of know something, and you could like put this knowledge into the addition to your observed training data to account for that during the learning. And in the Bayesian setting, so we have the training data, we have this prior knowledge about the parameters. So we could, for any given parameter value, we could estimate them how likely this data is to be generated by this model or to be observed in this model. And the Bayesian learning says, okay, just calculate by this formula. So calculate the Bayesian formula that says what will be the distribution of the parameters knowing the data. So before knowing the data, we had some maybe uniform distribution. After knowing the data, this posterior distribution of parameters is, yeah, something, right? So we still kind of, given the data, we're still not sure from which model, from which parameter value the data was generated, but maybe this one is the most likely one, and the others are also like good fits, and this parameter is not a good fit. Yeah, so this is what the Bayesian learning suggests. And okay, so if you look at the maximum parameter estimation, we can expand this numerator here. The denominator doesn't matter, so we can expand the numerator, and this expands as the negative log likelihood loss that we usually optimize in deep learning, and some like logarithm of the prior, which we can call a regularizer. So it's some term that does not depend on the data, right? So it's some function of parameters, but not a function of the data. So we could kind of now connect or interpret the regularized training in deep learning as Bayesian learning with a prior, but it's not the full Bayesian learning in the sense of this posterior distribution, but kind of finding this CTAM-up point, which is the most likely explanation of the data given the prior. And I think what I would like to note in this setup regarding the deep learning is that the choice of the model family is also kind of our prior knowledge that we put in. So when we design a particular, when we choose a particular family or we design a model, we choose specific architecture. These are all sort of excellent ways to put the prior information into the learning. And in fact, in deep learning, this is a much better way and more understandable for us than to say what is a good prior over what is a good distribution over the weights of some neural network a priori. No idea, right? We just throw this as a black box because we want it to be general and learn what are the true dependencies and what are to kind of fit to the data. But we actually, it's not interpretable, right? What are these weights? So, and therefore we cannot really model well these priors in deep networks. So it's gonna work really in practice more from the point of view that we design good architectures and we condition the training well. That's the effect what we could benefit from. And this extra regularization, yes, we can do a little bit, but yeah, so we would hit the two problems, like really what is this what is a good prior, and even if we had a good prior, maybe we had some, I don't know, some powerful diffusion model or something for doing the prior, also kind of learned one. Maybe that would be some option to have some learned priors from much larger data, perhaps unsupervised. And then we would have some maybe computational problem actually how to utilize it, how to use it if it is some good prior. Yeah, so this we discussed about this point, but then the Bayesian learning actually tells us that if we have this distribution, we could do a bit more. So we could compute the expected prediction under this distribution of the models. So this is our example. So there are some data points, and we could fit different polynomials to these data points, which are all passing through these points. And maybe all of these models are likely according to the prior, but there are many, right? And then you could do the Bayesian prediction in terms of averaging of all predictors that which are sort of with their weights according to how well they are explaining the model. And this would be our Bayesian predictive. This black curve thing is sort of like average prediction, and you could then imagine that it is more robust, right? And sort of somehow more smooth and averages over like sort of conservative averages over all the predictions. And from the scatters, you can estimate not only the expectation, but also variance, for example. And then you will have scatter at the point, so you will have some quantified uncertainty. And again, this is nice, but derive back again these two questions. So how do we compute this? This is even difficult for simple models, but we can do stuff like Gaussian processes can do this exactly, and everything is computable. But it's still, there is a question, how do you choose and model the prior, right? So unless it is some model which is very clearly interpretable, we're going to have difficulties modeling the prior in the first place. But we will see that some techniques in the neural networks, some regularization techniques in neural networks kind of connect to this idea that you might have multiple good fitting models and you want to average over the models, and you can measure scatter over these models. So it is possible to approximate these things by different ways. But again, I would say that from the practical view, we should expect that the gain from this would be sort of smaller than the information that we could put into the model design and into like good training schemes and data augmentation and sort of these things. So yeah, so this was like a step to the classical machine learning and what is the best we would like to, and how now it relates to deep learning. And this maximum a posteriori solution, we said we can rewrite as the sum of these terms of the likelihood and the regularizer. And now let's have some parameter. Okay, how much we would like to regularize. And this is gonna be our regularized setup. This parameter from the Bayesian setting, we see that it should be something independent of the training size of the training set size. And kind of the regularization, the effect of the regularization should diminish if you have a larger and larger training sizes. And that makes sense. So if you have enough evidence to estimate your parameter precisely, you should rely more on the evidence rather than on this prior, right? In the Bayesian, from the Bayesian perspective. So this is natural to have this lambda like a constant independent of the size of your training data. But in deep learning, it's often rewritten in the form that you have some expected loss on your fixed size training set, and then the lambda is constant with respect to that. I mean, it is equivalent. So if a training set size is fixed anyhow, and you're gonna tune this regularization parameter anyhow, it is kind of equivalent. But if we are dealing with, I don't know, some like maybe stream of the data, or we are going to make some experiments with the variant data set size, it makes it reasonable to consider maybe rather this setup, which is consistent with the Bayesian interpretation. So now we have these simple ways to model this regularizer, and most popular and kind of efficient enough for shallow and deep models is this L2 regularization. So let's discuss what it is and what it is doing in classical models, and sort of stretch the interpretations what it is doing in the deep models. So we have just quadratic norm of the weight vector. And we know what it is doing in the linear regression, right? So in the linear regression, if we add such a thing to our L2 loss, then we know the solution. So we did that. And this solution, on one hand, we already discussed that even if you take a small lambda and the problem is overparameterized, then this solution helps to regularize this. This regularization helps to regularize this solution still, and the effect is that it will be sort of, if there is a space of optimal solutions, then the effect of the regularization is finding the closest. So this is the space where the loss function is minimized, right? And then the effect of the regularization is finding the parameter vector which is closest in this space to our initial point of initial zero vector parameterization. No, okay, so here it's without gradient descent, so just the one that is closest to the zero. And at this point is also somehow corresponds to the maximum margin in the classification. Here is one more interpretation, is that actually this regularization, so this is like also classical known fact, it can be reinterpreted as training with inputs perturbed by some noises. So we could formulate this problem as so this is like L2 loss between targets y, and instead of the predictor theta times like a linear predictor based on x. So here we are perturbing this x with some multiplicative noises, which are normally distributed with mean 1. So we kind of randomly perturbing the inputs and then multiplying, so then scalar product with our vectors. It's kind of linear predictor on the noisy inputs. And then we are looking at the parameters which minimize this loss in the expectation over the possible noises. So we are saying that, okay, not only we want to fit to all the original points, but we want a good fit also to sort of multiplicative to variants of this training set, which differ by a multiplicative noise on this point. So we want like a good fit to all these things, and then it's some not difficult exercise to see that then it is equivalent to this regularized problem. Yeah, also in linear classifiers, you know that support vector machines, they maximize the margin, and this is rewritten equivalently as some kind of data loss plus the norm of this weight vector. So actually minimizing this norm of the weight vector corresponds there to maximizing the margin. So this thing that you discussed. Now, what happens in deep networks? We could speculate a little bit on the level that, so suppose that all our weights are rather small and we are using this sigmoid or hyperbolic tangent nonlinearity, and then the pre-activation would be sort of distributed more or less in the linear regime of this hyperbolic tangent or sigmoid. And that means that we could look at this neural network in this near linear regime and ask the question, so what will happen with that model in this case? And then if you regularize the weights, so we try to shrink them, we try to make them smaller, then this is facilitated. So if the weights are smaller, then we are closer to this linear regime. And if you are closer to this linear regime, it's the whole composite network is kind of smoother, so it gives us smoother predictions, so less of the jumps in our decision boundary in the in the space of the inputs. There is also a more rigorous approach to this, explaining what the gradient descent is doing and how the neural networks are training in the regime where you have many hidden units. So in this over-parameterized regime, and more specifically, if you have even like the widths of this neural network go into the infinity. So assume you have some fixed number of layers and the up like infinitely many hidden units. And in this regime, it has been shown that gradient descent is actually can be reinterpreted equivalently as optimizing a linear model in some kernel space associated to this network, and this is this neural tangent kernel theory. It is beyond of our course, but the point here is that some of these arguments which I am given about the linear regression and about basic models, they can be applied to deep networks via this, at least via this neural tangent kernel theory and analysis. So sort of whatever we can say about the linear models would be also applicable to the deep models in the regime when the hidden size goes to the infinity, so that they could be well approximated by these linear models in this kernel space. Roughly, okay. I think at least on the level of the idea that somehow makes sense. I hope. All right. So yeah, what's next? In deep learning, this L2 regularization is somehow also often called weight decay, and let's see why. So this is quite straightforward. If we differentiate this, we obtain, okay, so let's apply gradient descent. So the gradient descent will the gradient will consist of two parts, of the loss function and of the regularizer. And the gradient of the regularizer is going to be like in the direction, so if you differentiate the squared norm of the weight vector, we get the weight vector out of it, right? And then the gradient descent will be stepping towards shrinking the norm of the weight vector, so that means towards 0. And if you make a step like having like our initial point and add this shrinking, so this looks like decay in the weight vector. So basically just multiplying it by some factor which is less than 1 at every step. So it kind of shrinks towards 0 at every step. And concurrently, we are making a step towards minimizing the loss. So this component. Yeah. So and then this is the picture that I already tried to discuss. That okay, now in the neural networks, especially in this regime when we have many neurons, there would be a manifold of optimal solutions, those which are attaining a zero loss. And in principle, we could be like finding any of these solutions, and maybe they are not good. So none of them could, not all of them could be generalizing well to the training data. But actually, by the dynamics of gradient descent, it turns out that we're going to be finding the solution that is closest to our initial point in the L2 norm. And this effect we could achieve in both ways. So explicitly by adding a regularizer to be closer to the initial point, like this L2 regularizer, or we will see that it is in the next lecture, that it is actually also implicit there. So the gradient descent is already has a little bit of this property that it will be finding this solution, even if we don't add anything here, just because the gradient descent is the steepest descent in the L2 norm. So the idea is that then if you find the point closer to 0, it will have like a smaller norm of the solution. So here the norm of this weight vector was growing and it was getting overconfident. Now if the norm is somehow penalized by this regularizer, so this will stop happening, and then the test loss maybe will not be growing unbounded, but it will be kind of stabilized somewhere. Okay, we can also view it from the following figure, what it is doing. Suppose this is our loss function, and we can imagine that the loss function is approximately a quadratic function. And now this is just kind of illustrative example where this quadratic function is aligned with the axis. And then in this example, what happens then if we do not regularize, so kind of we are in the global minimum of this quadratic loss function here. If we do add this quadratic regularization, then we find some point at which we could the contour lines of the regularizer. So this is our L2 ball of the regularizer, and the contour lines of the loss function, they are touching, right? So then these two gradients are in the balance. So this would be conditioned for the optimum, and they kind of we could actually even calculate in this case precisely what happens with this solution. So it is going to be the coordinates of the weight vector are going to be shrinking towards the 0, depending on the strength of the regularization and depending on the curvature of the loss function in that direction. So so here is high curvature in this direction. In the x-axis, it's a low curvature, and therefore they will be more shrinking in the x direction. So they kind of, in this case, in this axis aligned case, they independently shrink by this eigenvalues of the Hessian they describe in this curvature. Yeah, I'm not sure like why this is important by itself, but it's nice to compare then with the L1 loss. So then we will come to this. Right, so here's one illustration from a book on statistical elements of the elements of statistical learning. And it is an example similar to what we considered in the lab. There is some classification problem, there is some training data, which is maybe mixtures of Gaussians, but maybe with more components. There is a true optimal classification boundary given by this purple line. And they are fit in a neural network with one hidden layer that is doing embedding. So this is like the two coordinates on the input and the homogeneous one on the input. And then there is 10 hidden units. And this matrix shows the weights, right, for each output and for each input. This is the hidden layer, and then there is the output layer, which goes from this space, from the 10 hidden units to the two scores for the two classes. And these are the weights of this classifier layer. And the corresponding decision boundary is this black line, right? So this is like an unregularized solution. And then we add a little bit of the weight decay, and what we see is that all these weights become smaller. So then I guess, if I recall correctly, they were using these hyperbolic tangent hidden units. So the weights become smaller, we are closer to the linear regime of this network, the decision boundary becomes smoother, and so it's kind of less fractured like this. So it is a smoother and simpler decision boundary, still sort of fitting well to the training data, and that generalizes better. Right, now let's see how it works in contrast. So what if we change this norm? So if we change the regularizer, let's say we use one norm, it will be sum of absolute values of our parameter. Then in terms of this gradient, we see slightly different picture. So the gradient it is a sign of the weight vector. So whenever the weight vector has a non-zero component, they will be like a force or the step forcing it closer to zero, regardless of whether it was small or large. So in this example, like the step in the y coordinate would be larger than the step in the x coordinate. So it would be kind of proportional to how far the coordinate is from zero. But in this case, like for all of the coordinates, it pushes sort of equally. And the result of that is that the coordinates which are close to zero, so then they are still pushed with this substantial force to zero, and so they are likely to become zero eventually. And on this diagram, like balancing the level sets of the function versus the regularizer, you see that the optimum, so where these gradients are in balance, it is going to be attained rather in the corner, so in one of the corners of this ball of the L1 distance, right? So it is in 2D space. You could still imagine that it will be touching like this contour line would be touching here on the side. Yes, it's possible, but when the dimensions go higher and higher, this scene becomes sort of more and more pointy, so it is much most likely that it is going to be touching on the corner or on some facet, right? But not on the sort of full dimensional facet. And from this, we kind of immediately see that this is gonna do sparsity, right? So there is the L2 norm was promoting the weights to be small, but sort of evenly distributed. The L1 norm is rather promoting the solution to be sparse, that sort of many of the coordinates would just be 0. And I don't know, maybe it's not generally what we want for a better generalization. So you might want it for finding a more compact model. So if you start from some large space with many hidden neurons and many weights, so if we add this kind of regularization, it is likely to maybe not use a lot of weights and find a simple solution. That's one thing. But for this effect of averaging of many simple solutions, for this effect of interpolation, it is not going to work. So rather the L2 would work for that.
So it could be used, for example, for distilling like a bigger model into a smaller one. Like if we have an already trained model, could we like start like fine-tuning it with L1 regularization and then like drop the neurons which have 0 weight, something like that?
No, but I mean, you still have this. Yeah, yes, you can, but you can lose some generalization in principle. It might be good for distilling, right? So if you have the distilling target, then you have not only the individual labels of the training data, but you have the predictive probabilities, so the scores. So these conditions the training better, and maybe at the same time you then can try to reduce the model size and do the sparsity. Yeah, that makes sense. Yeah.
Some of them, which may be not advantageous, but generally when I hear L1 regularization, maybe not too late, but something else, it's usually, at least in my head, still connected to some robustness or something like that. Yeah. So
it could be. I mean, there could be different models and different effects, and maybe the things have multiple effects, right? So it's hard to disentangle. But from this point of view of training in this overparameterized mode, when you put more hidden units to have a more rich set of initializations, and then to allow the model average over all possible weak predictors, then this tends to generalize well. Whereas then if you infer sparsity, then it's opposite.
Wouldn't it make sense if we know that we are definitely not in the like really overparameterized mode? Because when we are in the like really overparameterized, let's say like the homework example with dimension 10,000, then definitely it would make sense to use L2.
Yeah.
But if the dimension is, let's say, 100, which is still like really strong overfitting, but not in the like double descent region, then it would make more sense to use L1 and let the optimizer like disable the weights that cause the overfitting. Wouldn't that make like sense? When to switch from L1 to L2?
Yeah, I would not dare to answer this. So I guess it would depend on the model and on the problem. It might be, yes. So I don't have such experience. Yeah, anyway, I mean, now that we've seen L1 and L2, it's a natural question what's in between. And yeah, we could put the P norm so that to take absolute value to the power P and then the square root of P. And this generates such unit balls. So the the 2 norm is circle, right? The 1 norm is this square, and the infinity norm is such a square. And yes, you could reason also in the opposite direction. So if you want the weights to be more evenly distributed, we would increase this power, and we would use some maybe 10 norm or the infinity norm. Yeah, so this is then up to the practice what what is going to work or improve something. But again, like from the theoretical side, we would know what it will do for linear models, and maybe you could this would give some insight and some idea. And for linear models, for binary classification problem with a linear predictor like this, and consider the regularized training with the p-norm regularization like this, then there is the following theorem that it is consistent what I've told you here, that the optimal solution even in the limit of this regularizer approach in 0. So if you add a little bit of the regularizer, but sorry, this picture. You add a little bit of the regularizer, but you are in this over-parameterized mode, so there are multiple optimal solutions. Then which solution this optimization will converge to, or what is the optimal point of this optimization? It is proven that it will be the sort of the closest point in that respective norm. So it is now not only the shortest in this 2 norm, but with respect to the p norm. See if it maybe if the coordinates are like this, so maybe the closest L1 norm will be here, right? It could be, I mean, depending on this picture, right? So this L2 and then L1 could be there. That's one thing. And the other thing is that if you look at the input space, so the separating hyperplane will be convergent to the maximum margin, but again, with respect to this norm. So if it is the 2 norm, then it will be the hyperplane that achieves the maximum distance to the 2 sets in the 2 norm, but it could be the other norm. And it does so. So we add a little bit of the regularizer, and we get like a maximum margin solution with that norm. While, what was it? Yeah, so this is sort of the limiting behavior that also shows that if we decrease the strength of this regularizer, then so that then the norm of this vector, the norm of the weight vector can be actually grow into infinity. No. So there is some contradiction to what I said, right? So it says the second thing says that it's the max margin separating hyperplane, but the first thing says, so this is contradicting to this picture that we are finding the closest point to the original one, because the norm is growing to infinity.
That's when the effect of the regularizer goes to 0. So that's like without the regularization, the weight would go to infinity. That's what it says. No?
Yeah, and that's bad, no?
I'm confused. I think it makes sense to me.
The first one is without regularization, the second one is with regularization.
Both are about this problem with this. So this is regularized solution as a function of the regularization strength, right? And this says that the direction of this weight vector is going to be the max margin separating hyperplane, but its norm is growing to the infinity. But it's still somehow inconsistent with the other results that we've been discussing. Because if the other result was saying that you will be convergent to this point in this space of the parameters. Yeah, okay, yeah, I will need to check. So there are interesting things to observe. And yeah, so we could pick up something from this analysis, from the linear classifiers, and also expect that, yes, so that if we play with this norm, then we will be, what we are playing with is that what kind of margin we would like to have in the input space, and what it will do for in terms of generalization. Okay, and then I played with the example from the TensorFlow playground. So anybody can play with this, but they don't have like a preset of like a good illustrative examples, really. So I made it the cases that we need for this lecture. So there are some two-dimensional inputs, and the first there is some fixed lifting. So there is like it's not only the features x1 but also x1 squared, and then the product and the sign of the two coordinates. So it's a fixed lifted space of features. And then there is a hidden layer, maybe with hyperbolic tangent units. And the network can learn all these weights and then all that weights. So this is then the solution without regularization. Now if we add L2 regularization, what we can observe here is that these weights, or we would hope to observe that the input weights to each of these hidden units are sort of more uniformly distributed, and the input weights to the last hidden unit are also like more uniformly distributed. Maybe it's not very clearly visible here, but if it is the case, that would mean that we are averaging over all possible features, and we are producing a smoother decision boundary, and here it is. So this is the points and the decision boundary. Whereas if we do L1 regularization, so what it does, that forces many of the weights to be 0, and it really finds some sparse solution. Maybe not too bad in terms of fit into the data, but in this case poorly generalizing, because okay, so it picks only some features, and these features do not happen to generalize well to that data set. Yeah, so that was the example. What we can do also, yeah, maybe very briefly about what more with these simple norm regularizations. So we discussed this p norm, right, and the effect of this ball. But then we have some structure in the neural networks. We have some inputs and we have some outputs. So then it is a natural idea to say that, okay, we want maybe these red weights which are coming into the same neuron to be more or less maybe evenly distributed, because it would use lots of features and average over all these features. Whereas maybe the weights coming into the different neurons, we don't necessarily to have them evenly distributed. So maybe the neuron of this neuron might have in general larger weights than this one. And then we could kind of separate on that basis. From the practical side, it gives rise to combinations like, okay, you take the maximum over this and then sum over the output units. There's something called max norm that was shown to be helpful, but maybe was not very popular. Yeah, I don't know. On the theoretical side, some result generalize on all these norms. So if you have the PQ norm, what they show that if you bound this PQ norm for all the layers and all the weights in this form, then you can bound the test risk in terms of your training risk plus this gaps in that generally is a function of the number of neurons in the network and the number of layers. But it turns out that because of this maximum here, the cap here, it turns out that this number of neurons is taken to the power 0 if the q is less than p over the p minus 1 in this norm. So, and then the other factors like would be diminishing with the number of training samples. So it's sort of, it tells you that the generalization of the models with the PQ norms satisfying this, you could expect good generalization according to this theorem. And if you don't have the q less equal than p over p minus 1, then you need not expect a good generalization. Well, that's a theory. Of course, it's not. It could be like quite far away from practice, but it also maybe guides the idea of how you choose the norms to experiment in practice. So the 2-2 norm, for example, satisfy this, but let's say the p equals 2 and q equals 3 does not, or the p equals 1 and q equals 2 does not. So that's this then could be maybe from this theory consider it as a not perspective or not promising choices for regularizing these models. Yeah, anyway, like, I mean, we have summarized what we know about all this P and PQ norms regularization, and then it's up to the experiments what works. So usually people don't bother with that, so that they would just add a little bit of this weight decay of the L2 regularization, and then this is the probably you cannot get much more out of it. Okay. So the next thing we are going to discuss is data augmentation. Yeah. Now maybe it's like rather straightforward, right? But let's try to systematize a little bit. I mean, the whole idea of the data augmentation is if you know the nature of your data and you know what kind of transformations are likely to produce to preserve your class labels. So if you are classifying, then we want still the transformation to preserve the class of the image. So if you rotate, you know it's still a cat. If you do a little bit of color jitter, yes, it is likely to still be a cat, but then there is a question, okay, is it still sort of a naturally looking image that we would expect in the test setting with that label? So there are these two sides. So to generate something which is likely in the manifold of your data and preserve the label if it is about classification, right? So we can do all these geometrical things like scale, crop, rotation, some photometric things, but maybe to limited extent. And yeah, so by doing this, we kind of generating more data, and we maybe even promoting some invariances or equivalences of the network. So if you train with all these rotated cats, then we would hope that at the test time, the classification would be robust, more robust to the rotation. Or if it is segmentation, that it would be more like, so they rotated, so this segmentation of the rotated image, we would like it to look like as a rotated segmentation of the original image. And yeah, so we could enforce these properties, that it can enforce maybe some robustness of the model to maybe different things, like some changes of the distribution, something. But there are also dangers or disadvantages. So if we alter this training distribution too much, then we are introducing a distribution shift. So that if during the training we have too much of this data augmentation, too much of the synthetic noises, then we are training actually on some distribution which we will not have at the test time. So we are introducing this distribution shift, and it could be even the thing that we don't notice as humans, but the machine learning picks up. For example, if we train on synthetic images which look very nicely and very rich in all the, so look very appealing to us, very quite rather natural. Still, the machine learning could pick up some, I don't know, regularities in the textures, in the how the images render it as opposed to the images taken from real cameras. And it turns out that there is still, it does introduce some distribution shift. So then if you test it on the real images, then it doesn't work that well. And of course, if we do a lot of this augmentation, it also costs us the computation time, right? So the more we augment, the more variants of this data we create, it could increase the training time. Oh, okay, yeah, it's a question. I mean, if you consider it as a well, there are trade-offs. So I mean, if you have a training budget of 100 epochs for ImageNet, then whether you do it without augmentation or with some random augmentation, it is still 100 epochs. But the question is like whether you will have improved performance in the same 100 epochs or not. And then maybe it will be like leading to slower training in the beginning, and then there are schemes like, okay, you do this augmentation progressively. So first you start training more with the clean data, and then progressively you add more of the sort of, you make the augmentations in a wider range. So then this helps. That yeah, usually it helps. The common scenario is if you can make your model larger, make it larger. If you can train with more data augmentation, which is relevant, train with more data. If you have more data, train with more data. If you don't have more data, train with some augmented data, and then this all improves. Now, I mean, to this point of the data augmentation, I think we could like connect this to our discussion of the symmetries and the equivalences. Yeah?
Okay, no, never mind. Maybe we'll actually get to that. But it just occurred to me that as you were saying that in like maximum margin classifier, that in regularization was equivalent to like adding some multiplicative noise to points.
Yeah. Yeah. Yeah, so some of so some of the data augmentation, which is as simple as multiplicative noise of the input, you can do it like that. So you could generate it and consider it as a data augmentation. But if you have a linear model, then you know that you could do it analytically also, so that you don't need to generate these noises, and so you could train directly.
As a mental model, not like a
Yeah, yes. So for the deep model, we don't have this close relation, so maybe multiplicative noise on the input, you cannot analytically transform it as some kind of regularizer on the weight parameter, so it might have sense to do that, and to do it via like this random generation. And similar with these equivalences, right? So we could have either equivalent network that by design classifies this image the same as this image, or segments, I don't know, equivalent, so invariant, let's say, invariant, and then classifies. Or we would need, or maybe if you don't have this property, we might need to kind of create, to handle it via data augmentation. So instead of just enforcing classification of this image only, we would generate also the transforms, which is kind of data augmentation. We know it is the transform, which preserves the label, and we ask the network to classify it again. Yes, we can enforce this via data augmentation, but if you had the translational invariance, this would be for free. We would not have to do this many data augmentation copies. And it's similar with this permutation invariances, right? So if you have a function which is the real function, we know it must be permutation invariant, but we are training some general function, then we could in principle generate the m factorial permutations and train with that, and it will achieve sort of via the learning, it will achieve this invariance, but it will cost us much more of these data augmentations. Yeah, that will take more time for sure. On the theoretical side, people have shown again for linear models, so that you could have a generalization guarantee on the risk. That is, what to say about this is that sort of this generalization bound gets tighter if you have symmetries, if you have these equivalences. So if there is the m factorial permutations, then the generalization bound for the model that is by design invariant to these permutations, then the generalization bound is much like an n factorial smaller, I guess, in this term, and also there is also some power. I don't want to talk about that. Yeah, there is a theoretical guarantee that says that if we have the equivalences by design, that you need less training data to generalize with the same guarantees. And that's like intuitively, that's very natural, right? What we discussed here. Yes, you can generate the data just by creating the permutations or the shifts. And obviously this will be that much more data. All right. Now the sort of another interesting practical trick is combining different data points. So before we were talking, let's take an image and do some transforms with that preserves the label. And now this one is a little different and smart in a way that says, okay, we're gonna take two images from our training set and combine them. And the combination is actually very simple one, to the point of being silly, because it says we just gonna have like a convex combination of these two images pixel wise. So we just blend them, and this is like then the blended image of the cat and dog. And the same, and moreover, the same we do with labels. So the labels could be written as one-hot vectors, and then we could have a, right, the convex combination of these one-hot vectors, and then this will be our training data point, which is 0.7 cat, right, and 0.3 dog, and the images are mixed with that coefficients and the labels are also mixed with these coefficients. So we could create such thing, which is, I think it is a little bit out of our manifold of the training data, right? On one side, and it does not preserve the label, so the label is also mixed on. So it is not that kind of data augmentation. So it's something else, and this something else, it's has the following interesting effect. So the way to understand how it works, I think, is, or it was the paper original explanation, is that it promotes linearity in the predicted probabilities. So suppose this was our training set. Again, this classifying to the points, like this basic example. So we had the orange points and the green points. And the blue thing is the trained predictor. And you see here this decision boundary is good. It's like maximum margin, but overconfident. Whereas if you added such augmentation, you request to predict convex combinations of these labels for the convex combinations of the inputs. And if you imagine here some connecting line and like a convex combination of these 2 points with the different coefficient, then what this target requires you is to predict a linear function between these 2 points. So you kind of, it enforces the model to be linear in the sense, or more linear in the sense that for if you yeah, so basically more linear in the sense of the mapping from the input space of the images to the space of these predictive probabilities. And this has, I would say, this has the effect connecting to the regularizations that we've been discussing before. So the L2 regularization that were kind of averaging over the predictors, and by this way constructing a more smoother combination of the predictors, more smoother boundaries. So this is sort of alternative way towards the similar effect. So to keep the model closer to the linear one, and by that obtain a smoother decision boundaries and maybe like control this overconfidence.
I think it's not quite the same. Like for both, you can say like smoother decision boundary, but one of them is like there's a clear boundary which is smooth, and here like there's like diffused boundary.
Yes, but they are displaying here this predictive probability distribution. You could still, the decision boundary is your classification that you thresholded at 0.5, right? So it would still be, yeah, something. But indeed, here we already had a good decision boundary. So, I mean, this would not have effect on the classification in this case, in this example. Yeah, what is missing is the reason in how it could improve for more complicated cases, right? So what would it do for such a region where if you overfit, you kind of classify this as a blue class, right? But if you enforce these augmentations, if you enforce these linearities, perhaps this region of classifying this as a blue shrinks or even vanishes from the decision boundary. Maybe not vanishes if you are able to overfit. Yeah, okay. So practically, maybe you know, so the data augmentation is our second best strategy after designing the good model and exploiting all the real data. Then, yeah, so but it costs something. So okay, so this weight regularization does not cost much. We can always add a little bit of that. This costs something. Could improve if we control the data augmentation right. Then there is also this idea of injecting the noises. And the noises we can inject in many places, interestingly. So we can inject them into the inputs. And so the ridge regression was the example for the linear models. We can inject them in the deep features. We can inject the noises in the parameters. And we can even inject the noises in the gradient updates. And all of that is useful, and all of that can be used to improve generalization. And later two things, or maybe even the deep features in. So if this is going to be drop out, like injecting in the hidden units. So all these later three things can be actually related to the Bayesian learning ideas that we've discussed in the beginning, and to finding sort of more robust local minima of our loss function, but also they could be used to do this sort of averaging over multiple predictors, or in the case of this gradient updates, there are rigorous results that you could not to compute this posterior distribution of the parameters, but you would be able to sample from this, right? So you run the training procedure with the noise added to the gradient descent, and it will stochastically infinitely jump in the parameter space, but it will be jumping so that different points you repeatedly see with different probabilities, and this probability distribution will be the Bayesian posterior if you inject the right type of noise there. Yes, that's called stochastic gradient Langevin dynamics, but we are not talking about that. What we want to talk about is this basic classical technique, dropout. It's a very simple idea that says, okay, we're going to have multiplicative noises, which are just Bernoulli, so 0, 1. Either switch weight, so you could either consider them as multiplicative noises. No, sorry. Either switch or on or off the neurons in the preceding layer. So if at random this neuron is masked, then the neurons in the next layer don't receive any input from that, so they are kind of multiplied with 0. So instead of this signal, this unit is sending 0, and then all the weights connecting to the layers above multiplied with 0. So we kind of randomly dropping the neurons. And what we had as a result? Every time we drop some random subset of these neurons in every layer, we obtain kind of subnetwork, right, of the original network. And therefore, we could see this whole scheme as, and we are making a gradient descent step for this subnetwork, right? So we could see this scheme as that at each iteration, we are generating a random subnetwork of the weights. So the weights we still select from our common global subset, but we are kind of, every time we are generating a random subnetwork and making a gradient descent step for that, training that subnetwork. But at the test time, we are going to use the whole network with all the weights. So we sort of combine all these subnetworks back into one interconnected ensemble, so it's not just the sum of all these subnetworks on the output, it is the sum in every neuron. So there is kind of ensembling on the level of individual neurons from all these kind of subnetworks that we were training by individual gradient descent steps. Conceptually, it's also sounds appealing in the sense that yes, so we have this big neural network, and then one neuron should not be decisive, so we want it to be robust to if one neuron does not send the signal, or few of the neurons do not send the signal, so we want the network to be robust to such perturbations. And then let's make this training robust. So then during the training, we kind of bombard it and by destroying some neurons randomly, and we want it still to train. And maybe by doing that, we hope that it will be more robust at the test time as well. Okay, so what we can say about this process of sort of selecting these subnetworks and then in the test time combining this whole scene into one network, what we can say about this in equations. So in terms of equations, we can do it as follows. All right. I need to wrap it up maybe quickly. So the switching and on and off dropping randomly these hidden units, we will model as Bernoulli random variables. And then during the training, we are doing the following. So we look at the expected loss of the network with these Bernoulli variables, denoting which units are on and off. And we're gonna look at the expectation of this whole loss with respect to the noises as well, so like the total expectation. And of course, to optimize this, we can do also by stochastic gradient descent. So at each iteration, we need to sample the mini batch of the data, and we need to sample these Bernoulli variables. And we can make a step on optimizing the loss for that network. And the effect of that is that we are optimizing this total expectation of the neural network with randomly disabled neurons. At the test time, we want to look at the expected predictor. So we still have this predictor that depends on these Bernoulli variables, like this one specific subnetwork selection. And at the test time, we would want to look at the expected prediction. So what is the prediction of all of these possible choices of subnetworks on average over these Bernoulli noises? And this is connecting to this Bayesian averaging, right? So that we have many models fit into the data. So for every realization of this random noise, maybe we have it robust, so it is predicting well for the training the training data. And now we are averaging over all of these predictors to get in sort of average and a more better generalizing predictor. And in the simple approximation, we can push these expectations through the nonlinear neural network function down here. And then what we are doing, we are replacing these Bernoulli variables with the expected values. And then simply it means that, okay, whenever we had these Bernoulli dropout variables with probability 0.3, then its expected value is the probability, is the 0.3. That means that at the test time, we're gonna multiply the output of this unit by the 0.3, right? So it could be during the training, maybe on average there was a sum of only 1/3 of the inputs because the 2/3 were disabled. But at the test time, we take all of the weights, and then it will be more of them, right? So we need to kind of downweight this to have the pre-activation here on the same scale. And this corresponds to putting this expectation here. But so this is like one basic approximation which is commonly used. But we can even sample this. So we could like, okay, instead of just doing this cheap approximation, we could just really at the test time also drop the units at random and just compute the average prediction of this. So doing the Monte Carlo approximation of this expectation. Maybe this is a little bit more costly, but possibly it could have some benefits. And yes, it generalizes a little bit better than this above seen. But actually for common deep models, the difference is small. So people tried it to do for the regression models for some toy problems. And in this example, there is a substantial difference. And so the example is, yes, we have this training data. There is maybe some true function from which this training data is sampled, but we don't know that. And clearly, to this training data, you could fit many nonlinear models, right? That pass close to all of these training data points. But then what you like to do in the Bayesian setting is to have some posterior distribution over the models and to have the average predictive curve. And this dropout kind of does something sort of similar in the way that we are fitting the network such that it fits to the training data. It means it is, regardless of these Bernoulli noises, the fit to the data is good, which means we are sort of somewhere here, right? So it means that the test likelihood is good for all these models. But there is still diversity of the models. And some of these models happen to pass here, and some of them there. And so sort of there is this uncertainty or diversity in this among these predictive models. So it's good to take average of them. And moreover, this diversity can be used to quantify the scatter, to quantify the uncertainty of this prediction. Yeah, this looks nice, but of course we also realize that there is no reference for this. So what is the correct uncertainty prediction? Nobody is able to tell because it is all with respect to the prior and with respect to the concrete model, even if it is to be computed correctly. But yeah, so dropout is considered as one possible ways of sort of modeling uncertainty through this mechanism. That, okay, it's randomized at the training time, and then if you like consider it as a randomized at the test time, and then you could look at the expected prediction, and you could look at the scatter of the predictions. So I stop here. I had some more examples for what it does and for batch norm. Okay, that's it.